This chapter discusses the fundamental concepts of database management. It is based upon our book, Principles of Database Management. You can find more details about our book on the website at the bottom of my slide. My name is Bart Baasens, and I'm one of the co-authors of the book. We kick off by reviewing popular applications of database technology. This is followed by defining key concepts, such as a database and a database management system, or DBMS. Next, we step back in time and discuss the file-based approach and contrast it with the database approach to data management. We then zoom into the elements of a database system. The chapter concludes by discussing the advantages of database design and database management. Data is everywhere and comes in different shapes and volumes. These data need to be stored and managed using appropriate data management or database technologies. Think about the storage and retrieval of traditional numeric and alphanumeric data in an application developed to keep track of the number of products in stock. For each product, the product number, product name, and available quantity needs to be stored. Replenishment orders need to be issued as soon as the quantity drops below the safety limit. Every replenishment order has an order number, order date, supplier number, supplier name, and a set of product numbers, names, and quantities. Database technology is not just for traditional numeric and alphanumeric data. It can also store multimedia data, such as pictures, audio, or video. As an example, YouTube or Spotify support the querying of music based upon artist, album, genre, playlist, or record label. Biometric data, including fingerprints and retina scans, are often used for security, such as border control as you enter a country. Similar information is gathered by wearables, such as a Fitbit or an Apple Watch, that continuously monitor and analyze your health and fitness. Geographical information systems, or GIS applications, such as Google Maps, store and retrieve all types of spatial or geographical data. Database technology can also store and retrieve volatile data. A popular example is high-frequency trading, where automated algorithmic platforms are used by investment banks or hedge funds to process a large number of orders at extremely high speed based upon events happening in the environment or macroeconomy. Also think about sensors monitoring the key parameters of a nuclear reactor, whereby an automatic system shutdown may be decided if certain thresholds are hit. You may have heard of the term big data, referring to the huge amounts of data being gathered by companies. Consider the data collected and analyzed by Google, Facebook, and Twitter daily. For example, look at Walmart, America's largest retailer with over 11,000 locations worldwide, $4.8 billion in annual sales, and over 100 million customers per week. Its point of sale POS database system stores an enormous amount of data reflecting which customer bought what products in what quantities at which location and what time. All this data can then be intelligently analyzed using analytical data modeling to unveil unknown yet interesting purchase patterns, such as which products are frequently purchased together. Better still, certain analysis techniques allow for making predictions about the future, such as which customers are most likely to respond positively to a promotion. These are just a few examples of database applications, and many others can be thought of. We briefly introduced the concept of a database by exploring the various types of databases you may encounter every day. A database can be defined as a collection of related data items within a specific business process or problem setting. Consider a purchase order system, where you have data items such as products, suppliers, and purchase orders. Each data item has characteristics. A product has a product number, product name, and product color. A supplier has a supplier name and a supplier address. A purchase order has a purchase order number and purchase order date. These data items are also related. A product can be supplied by one or more suppliers. A purchase order is always connected to exactly one supplier. A supplier can supply one or more products. These are examples of relationships between the data items that should be adequately captured by a database. A database has a target group of users and applications. Think about an inventory manager who uses our purchase order system to manage the inventory and issue purchase orders. Or consider a product manager who uses it for monitoring trends in product sales. A database management system, or DBMS, is the software package used to define, create, use, and maintain a database. It typically consists of several software modules, each with their specific functionality. Popular DBMS vendors are Oracle, Microsoft, and IBM, whereas MySQL is a well-known open source DBMS. The combination of a DBMS and a database is then often called a database system. Before we further explore database technology, let's step back and see how data management has evolved. This will allow a proper understanding of the legacy problems many companies are still facing. In the early days of computing, every application stored its data into its own dedicated files. This is known as a file-based approach and is illustrated here. Suppose we have a traditional invoicing application written in programming languages such as COBOL or C, for example, that makes use of customer information such as customer number, customer name, VAT code, etc., stored in a separate file. A separate application, such as a customer relationship management or CRM system, makes use of a different file containing the same data, such as customer number, customer name, turnover, etc. Finally, a third application, for example a GIS application, stores information such as customer number, customer name, and zip code in yet another file. The data files only contain the data itself. The data definitions and descriptions are included in each application separately. An application can make use of one or more files. As more applications are developed with corresponding data files, this file-based approach to data management will cause serious problems. Since each application uses its own data files, many using similar data, duplicate or redundant information will be stored, resulting in a waste of storage resources. If this is not appropriately managed, there is a danger that customer data is updated in only one file and not elsewhere, yielding inconsistent data. In this file approach to data management, there is a strong coupling or dependency between the applications and the data. A structural change in a data file necessitates changes in all applications that use it, which is not desirable from a maintenance perspective. It is hard to manage concurrency control or the simultaneous access by different users or applications to the same data without conflicts. For example, if one application performs a cash transfer, whilst another application calculates the account balance, and the data operations of both applications are interleaved for efficiency, then this can easily lead to inconsistent data in cases where there are no adequate concurrency control facilities provided. Finally, since the applications each work independently with their own ecosystem of data files, it is hard and expensive to integrate applications aimed at providing cross-company services. Although this file approach to data management has serious disadvantages, many firms still struggle with legacy file-based systems in their current information and communications technology environment. The emergence of database technology provided a new paradigm for data management. In this database approach, all data is stored and managed centrally by a DBMS as illustrated here. The applications now directly interface with the DBMS instead of with their own files. The DBMS delivers the desired data upon request to each application. The DBMS stores and manages two types of data, raw data and metadata. Metadata refers to the data definitions that are now stored in a catalog of the DBMS. This is a key difference with the file approach discussed earlier. The metadata is no longer included in the applications, but is now properly managed by the DBMS itself. From an efficiency, consistency, and maintenance perspective, the database approach is superior to the file approach. The database approach results in a loose coupling between applications and data. It also provides user-friendly and efficient facilities for data querying and data retrieval. In the file approach, every application had to explicitly write its own query and access procedures. Consider the following example to the left in pseudocode. Basically, we first open a customer.txt file and read the first record. We then implement a while loop that iterates record by record through the file until the end of the file, as indicated by EOF customer, is reached. If the desired data is found, customer.name equals Bart, it will be displayed. Obviously, this requires a lot of coding. Because of the tight coupling between data and applications, many procedures would be repeated in various applications, which is again not very appealing from a maintenance perspective. DBMSs provide database languages that facilitate both data querying and access. A well-known language is Structured Query Language, or SQL. As the term suggests, SQL can be used to formulate database queries in a structured and user-friendly way. It is one of the most popular data querying standards used in the industry. An example SQL query that gives the same output as our pseudocode to the left is shown to the right of my slide. Here, You only need to specify what information you want. In our case, we want all customer information for customer Bart. This SQL query will then be executed by the DBMS in a transparent way. In the database approach, we only need to specify what data we are interested in and no longer how we should access and retrieve it. This substantially facilitates the development of database applications because we no longer need to bother with writing complex data retrieval procedures. In what follows, we discuss the elements of a database system: database model versus instances, data models, the three-layer architecture, the role of the catalog, the various types of database users, and DBMS languages. In any database implementation, it is important to distinguish between the description of the data, or data definitions, and the actual data itself. The database model, or database scheme, provides the description of the database data at different levels of detail and specifies the various data items, their characteristics and relationships, constraints, storage details, etc. The database model is specified during database design and is not expected to change too frequently. It is stored in the catalog, which is the heart of the DBMS. The database state then represents the data in the database at a particular moment. It is sometimes also called the current set of instances. Depending upon data manipulation, such as adding, updating, or removing data, it typically changes on an ongoing basis. Here you can see some examples of data definitions which are an essential part of the database model stored in the catalog. We have three data items: student, course, and building. Each of these data items can be described in terms of its characteristics. A student is characterized by a number, name, address, and email. A course by a number and name, and a building by a number and address. Here you can see an example of a corresponding database state. You can see that the database includes data about 3 students, 3 courses, and 3 buildings. A database model is comprised of different data models, each describing the data from different perspectives. A good data model is the start of every successful database application. It provides a clear and unambiguous description of the data items, their relationships, and various data constraints from a particular perspective. Several types of data models will be developed during a database design process. A conceptual data model provides a high-level description of the data items, such as supplier, product, with their characteristics, such as supplier name, product number, and relationships, such as a supplier can supply products. It is a communication instrument between the information architect and business user to make sure that the data requirements are adequately captured and modeled. Therefore, the conceptual data model should be implementation independent, user-friendly, and close to how the business user perceives the data. It will usually be represented using an enhanced entity relationship, or EER model, or an object-oriented model. A logical data model is a translation or mapping of the conceptual data model towards a specific implementation environment. The logical data items may still be understood by business users, but are not too far removed from the physical data organization. Depending upon the ICT environment available, it can be a hierarchical, codicil, relational, object-oriented, extended relational, XML, or NoSQL model. The logical data model can be mapped to an internal data model that represents the data's physical storage details. It clearly describes which data is stored where, in what format, which indexes are provided to speed up retrieval, etc. It is therefore highly DBMS specific. The external data model contains various subsets of the data items in the logical model, also called views, tailored towards the needs of specific applications or groups of users. The three-layer architecture is an essential element of every database application and describes how the different underlying data models are related. You can see it illustrated here. Let's start with the conceptual logical layer. Here, we have the conceptual and logical data models. Both focus on the data items, their characteristics, and relationships without bothering too much about the actual physical DBMS implementation. The conceptual data model should be a user-friendly, implementation-independent, and transparent data model constructed in close collaboration between the information architect and business users. It will be refined to a logical model based upon the implementation environment. In the external layer, we have the external data model, which includes views, each offering a window on a carefully selected part of the logical data model. A view describes the part of the database that a particular application or user group is interested in, hiding the rest of the database. It's used to control data access and enforce security. The views will be tailored towards the data needs of an application or group of users. A view can serve one or more applications. As an example, think about a view offering only student information to a student registration application, or a view offering only building information to a capacity planning application. Finally, the internal layer includes the internal data model that specifies how the data are stored or organized physically. Ideally, changes in one layer should have no to minimal impact on the others. It should be possible to physically reorganize the data with minimal impact on the conceptual, logical, or external layer, physical data independence. Likewise, changes to the conceptual logical layer can be made with minimal impact on the external layer, logical data independence. We elaborate on both types of data independence in what follows. This figure illustrates the three-layer architecture for a procurement business process. The conceptual logical layer defines the data items such as product, customer, invoice, and delivery. The internal layer contains the physical storage details specifying how and where the data is stored. The external layer has three views offering specific information to the finance, customer service, and logistics department. This three-layer database architecture has several advantages in terms of efficiency, maintainability, performance, security, etc. The catalog is the heart of the DBMS. It contains the data definitions or metadata of your database application. It stores the definitions of the views, logical and internal data models, and synchronizes these three data models to make sure their consistency is guaranteed. Various types of users interact with the database. An information architect designs the conceptual data model. He or she closely interacts with the business user to make sure the data requirements are fully understood and modeled. A database designer translates the conceptual data model into a logical and internal data model. The database administrator, or DBA, is responsible for the implementation and monitoring of the database. He or she sets up the database infrastructure and continuously monitors its performance by inspecting key performance indicators such as response times, throughput rates, and storage space consumed. The application developer develops database applications in a general purpose programming language, such as Java or Python. He or she provides the data requirements that are then translated by the database designer or DBA into view definitions. The business user will run these applications to perform specific database operations. He or she can also directly query the database using interactive querying facilities for reporting purposes. Every DBMS comes with one or more accompanying database languages. The data definition language, DDL, is used by the DBA to express the database's external, logical, and internal data models. These definitions are stored in the catalog. The data manipulation language, DML, is used to retrieve, insert, delete, and modify data. DML statements can be embedded in a general purpose programming language or entered interactively through a front-end querying tool. Structured Query Language, SQL, offers both DDL and DML statements for relational database systems. Databases, if adequately designed and managed, offer various advantages, such as data independence, managing structured, semi-structured, and unstructured data, database modeling, managing data redundancy, specifying integrity rules, concurrency control, backup and recovery facilities, data security, and performance utilities. We elaborate on this in what follows. Data independence refers to the fact that changes in data definitions have minimal to no impact on the applications using the data. These changes may occur both in the internal or conceptual logical layer. Physical data independence implies that neither the applications nor the views or logical data model must be changed when changes are made to the data storage specifications in the internal data model. For example, think about reorganizing the data across different storage locations or media, the definition of new access paths or indexes, etc. The applications will keep running successfully, maybe even faster than they were before because of the physical reorganization of the data. To adequately guarantee physical data independence, the DBMS should provide interfaces between the logical and internal data models. Logical data independence implies that software applications are minimally affected by changes in the conceptual or logical data model. As an example, consider adding new data items, characteristics, or relationships. The views in the external data model will act as a protective shield and mitigate the effect of these modifications on the applications. To guarantee logical data independence, DBMS must provide interfaces between the conceptual logical and external layer. Remember, a data model is an explicit representation of the data items together with their characteristics and relationships. It can also include integrity rules and functions. A conceptual data model should provide a formal and perfect mapping of the data requirements of the business process and is made in close collaboration with the business user. It is then translated into a logical data model and finally, an internal data model. Unfortunately, as we will see later, a best-case scenario with a perfect mapping is often unrealistic, and it will be important that a data model's assumptions and shortcomings are clearly documented. Popular examples of data models are the hierarchical model, the codicil model, the EER model, the relational model, and the object-oriented model. It is important to note that not all kinds of data can be described according to a formal logical data model. This is only possible for structured data, which was the only kind of data the earlier DBMS implementations focused on. With structured data, individual characteristics of data items can be identified and formally specified, such as the number, name, address, and email of a student, or the number and name of a course. The advantage is, as explained earlier, the ability to express integrity rules and in this way enforce the correctness of the data. It also facilitates searching, processing, and analyzing the data because both the DBMS and the data processing applications have fine-grained control over the data. They can, for example, discriminate between a series of characters representing a student's name and a student's address. In this way, it becomes possible to retrieve all the names of students that live in New York, for example. With unstructured data, there are no finer-grained components in a file or series of characters that can be interpreted in a meaningful way by a DBMS or application. Think, for instance, of a long text document containing the biographies of famous New York citizens. In this plain text, it is impossible to search for the terms name, student, and New York occurring closely together, but it is impossible to assess whether they pertain to students who lived in New York, students who were born in New York, or maybe even students for which the text explains they always wear the same sweater with the imprint New York on it. Moreover, it is not possible to retrieve only the series of characters that represent these students' names. In spite of that, many recent database management systems provide facilities to efficiently store and search such full-text documents. This is especially important since the volume of unstructured data largely surpasses that of structured data in most organizations. This unstructured data may contain lots of useful information if it can be extracted efficiently. Think, for example, of improving customer interaction by storing and analyzing complaints letters, classifying legal documents according to their content, or assessing the market sentiment towards a new product by analyzing tweets that refer to the product. Moreover, modern-day DBMSs are not restricted to storing and managing unstructured textual data, but other kinds of data as well, such as still images, video, and audio. It should be stressed that not all data is completely structured or completely unstructured. Recent DBMS types, such as XML databases and NoSQL databases, aim explicitly at dealing efficiently with semi-structured data. This is data which does have a certain structure, but the structure may be very irregular or highly volatile. Typical examples are individual users' web pages on a large social media platform or resume documents in a human resources database, which may loosely exhibit the same structure, but which do not comply entirely with a single rigid format. Remember that one of the key drawbacks of the file approach to data management was undesired duplication of data, which could easily lead to inconsistent data. In the database approach, redundant data can be successfully managed. Duplication of data can be desired in distributed environments to improve data retrieval performance by providing local access to data rather than using resource-intensive network connections. The DBMS is now responsible for the management of the redundancy by providing synchronization facilities to safeguard data consistency. As an example, an update of a local data copy will be automatically propagated to all duplicate data copies stored at other locations. Compared to the file approach, the DBMS guarantees correctness of the data. It also requires no user intervention and is much more efficient and less error-prone. Data integrity rules can also be explicitly defined. These rules can be used to enforce the correctness of the data. Syntactical rules specify how the data should be represented and stored. Examples are: customer ID should be represented as an integer. Birth date should be stored as month, day, and year. Semantical rules focus on the semantical correctness or meaning of the data. Examples are: customer ID should be unique. Account balance should be bigger than 0, and a customer cannot be deleted if he or she has pending invoices. In the file approach, these integrity rules had to be embedded in every single application. In the database approach, they are specified as part of the conceptual, logical data model and are stored centrally in the catalog. This substantially improves the efficiency and maintainability of the applications, since the integrity rules are now directly enforced by the DBMS whenever anything is updated. In the file approach, the applications themselves had to explicitly manage all integrity rules, resulting into a lot of duplication of code with the accompanying risk of inconsistencies. A DBMS has built-in facilities to support concurrent or parallel execution. Let me do that again. A DBMS has built-in facilities to support concurrent or parallel execution of database programs that allows for good performance. A key concept is a database transaction, that is a sequence of read-write operations considered to be an atomic unit in the sense that either all operations are executed or none at all. Typically, these read-write operations can be executed at the same time by the DBMS. However, this should be carefully supervised to avoid inconsistencies. Here you can see an example of two database transactions, T1 and T2. Transaction 1 updates the account balance by withdrawing $50. Transaction 2 deposits $120. The starting balance is 100. If both transactions would run sequentially instead of parallel, the ending balance should be 100 minus 50 plus 120, or 170. Let's now see what happens if the DBMS interleaves the actions of both transactions. T2 reads the balance at T2 and finds it, do that again. Transaction 2 reads the balance at T2 and finds it is 100. Likewise, transaction 1 reads the balance at T3 and finds it is 100. At T3, transaction 2 updates the balance to 220. However, it still needs to write or save this value. At T4, transaction 1 calculates the balance as 100 minus 50 equals 50, whereas transaction 2 saves the balance, which now becomes 220. Transaction 1 then saves the balance as 50 at T5. It overwrites the value 220 to 50, after which both transactions are ended. Since transaction 1 updates the balance based upon the value it had before the update by transaction 2, and then writes the updated balance after transaction 2 is finished, the update effect of transaction 2 is lost. It is as if transaction 2 did not take place. This is commonly called a lost update problem. Hence, the DBMS should avoid these inconsistencies that emanate from the interference between simultaneous transactions. To ensure that database transactions are processed in a reliable way, the DBMS must support the asset properties: atomicity, consistency, isolation, and durability. Atomicity, or the all or nothing property, requires that a transaction should either be executed in its entirety or not at all. Consistency assures that a transaction brings the database from one consistent state to another. Isolation ensures that the effect of concurrent transactions should be the same as if they would have been executed in isolation. Finally, durability ensures that the database changes made by a transaction declared successful can be made permanent under all circumstances. Another key advantage of using databases is the availability of backup and recovery facilities. These facilities can be used to deal with the effect of loss of data due to hardware or network errors or bugs in system or application software. Typically, backup facilities can either perform a full or incremental backup. In the latter case, only the updates since the previous backup will be considered. Recovery facilities allow to restore the data to a previous state after loss or damage occurred. Data security can be directly enforced by the DBMS. Depending upon the business application considered, some users have read access, whilst others have write access to the data. This can also be further refined to certain parts of the data. Trends such as e-business, B2B, business to business, B2C, business to consumer, and CRM stress the importance of data security because they increasingly expose databases to internal and external parties. Consider the example of vendor-managed inventory, or VMI, where a company can get access to inventory details of its downstream supply chain partner. Using the right security policies should enforce that only read access is provided and no information from competitor products can be retrieved. Data access can be managed via logins and passwords assigned to users or user accounts. Each account has its own authorization rules that can again be stored in a catalog. Three key performance indicators, KPIs, of a DBMS are the response time, the throughput rate, and the space utilization. The response time denotes the time elapsed between issuing a database request, such as a query or update instruction, and a successful termination thereof. The throughput rate represents the transactions a DBMS can process per unit of time. Space utilization refers to the space utilized by the DBMS to store both the raw data and the metadata. Obviously, a high-performing DBMS is characterized by quick response times, high throughput rates, and low space utilization. DBMSs come with various types of utilities aimed at improving these three KPIs. Examples are utilities to distribute and optimize data storages. Let me do that again. Examples are utilities to distribute and optimize data storage, to tune indexes, for faster query execution, to tune queries to improve application performance, or to optimize buffer management. These utilities are typically managed by the database administrator or DBA. We can conclude this introductory chapter. We started by summarizing some key applications of database technology. We defined the concepts of a database, DBMS, and database system. We then reviewed the file approach to data management and contrasted it with the database approach. We reviewed the elements of database systems. The chapter was concluded by discussing the advantages of database systems and database management. If you want more information, we are happy to refer to our book, Principles of Database Management. You can find more information on the website at the bottom of my slide.